We are continuing our study for database management systems with relational algebra. So far we've gone through a lot. The section that we're focusing on in this video is going to be join. This is kind of stemming off of our previous videos in the playlist link below the like button with Cartesian products. So join is like using Cartesian products but better. So an example for this is if we have like a element right here that we have imp dependence, and we have our imp names multiplied by our dependent. We've gone over this previously, and it's being stored inside of here. And then our actual dependence is where we get all of our columns here. And then our actual dependence, we are going to get the columns of our SSN equaling to our ESSN of our emp dependence. So all of these inside of here is going to go right here. We're assigning it, putting this basically in here. We get the columns for this, and we put it in actual dependence. We can replace this with a single join operation. So we have our actual dependence right here, and then on the right, what we're assigning it to is a emp names. So we have our emp names, and we have this join of our SSN and our ESSN right here with the dependent. So it's just an easier way to write it. If this combination is illegal, it's just going to get ignored. A join operation on two relations look like this. So if we have two elements R and S and we have these attributes inside of them, it's going to look like this. R, we have our join symbol, the condition, S, and this would be like our example. We're combining our X and Y. Everything must be distinct. Where R and S can be any relations that result from general relational algebra expressions. So we have like a condition, we can have an and condition, another condition, and so on and so forth that we join these together. So each condition is going to look like this. We have our AI, this is the attribute of R, or we can have like BJ, attribute of S. AI and BJ must have the same domain, so they also must be like the same compatibilities, like string, double, float, integer domain-wise. And then we have all these different symbols that we could replace this with, and that can be our condition. A very common one is the equijoin. If we have an equal sign, it's very popular, the join conditions with equals only. So an example here is like we have a department manager, we have our department, we have our join, and then we have the manager SSN, and then we have our employee. This result is an equijoin. We always have one or more pairs of attributes that have identical values in every tuple. We also have a natural join, and with this natural join, it's going to be represented by this asterisk, kind of like a multiplication sign. It's an equijoin without superfluous attributes. Any two join attributes have the same in both relations. So for join attributes, we are going to be equating all attribute pairs that have the same name in the two relations. So they're going to be equal. We want to rename when necessary before applying the natural join, just because we don't want any confusion. We can't have two of the same thing. So if we have like department locations, we have our department times our department locations inside of here filled out completely. We don't need a condition underneath because these are the exact same when we use our natural join. So for like example, if we have like the department and department locations that these are both being stored in, we have our D name, D number, manager SSN, and manager start date. Notice how our D numbers are the same for both of these. So we have department and department locations. We're multiplying them together. That means we just want to combine these tables. Well, if we're multiplying them together, well, we have to combine the numbers, right? So for all scenarios of research, we know that dnum is 5. So these are all going to be for Bel Air, Sugarland, and Houston. We're going to have multiple tuples of these. Then we have our admin, 4, it's just 1, and then our HQ, which is 1 here. It's good to use natural join since different tables have the same attribute. Q is just going to be the department times our department locations. So between the two, at least one pair needs to match. We need to decide if we do or don't want to join, and that would give us this table. Another example is if we have this RAB and this SBDF. So what are some ways we can do this? Well, we can easily just do R times S. This way, R, we have our join symbol, B equals B is incorrect. And this is because the query must know where everything comes from. It's not going to know which B belongs to R or S. So if we want to do it like that, we have to do something like this, where we have R, our join, and then S.B, and then a R.B. That way we know where each of them comes from. If we wanted to rename this, we could have something like this, and it would look like this. That's the result being stored here. These two are very complicated. If we have different names, like we had D number and like dnum, they're different, we can easily just do something like this. this is valid. And this is if they have different names. Otherwise, we should use our first one. So these two are the only ones that we should be focusing on using. If they have the same name, we should use Equijoin. If they have different names and we want to match and combine things, let's just use natural join. So that's a way we can look at this. Lastly, we have join selectivity. So we have our join condition, and then we have our join symbol right here. The join symbol, we're just going to always put it in front like this, and then we have our S. If we want to combine something from our R and S, R has NR tuples, S has NS tuples. The result is going to be a minimum. It's going to be an empty relation with 0 tuples. That's if we have nothing that's the same. No combination of tuples satisfies our join condition. That proves that right here. And then if we have a max, it's just going to be the NR times our NS. The maximum we can have is the maximum of these two multiplied together. And those are our section of notes. Lastly, we're going to complete set of relational operations, go over all this, and finish off our database management systems with our relational algebra.